or Unit 10, what we're going to focus in on. All right? And so let's go ahead to the Lord in prayer, and then we'll get to this material. Dear Heavenly Father, I do thank you for this day. I thank you, Father, for my students. God, I thank you, Father, for their ability to be here, to learn, to try, and to succeed. Father, I pray that as this week I know is very busy for them, as they finished some biology exams and there are other things that are upcoming, I pray, Father, that you will give them strength. I pray, Father, that you'll give them wisdom. I pray that you will allow them to find time for you, even in the midst of studying, Father, so that they can hear your voice. They can feel your spirit. They can have that calming peace of your Holy Spirit upon them. I pray, Father, that as we move through this material, that I explain it in a way that they understand, that they can see, they can think about what's happening, Father, all around them on the molecular level, so that we can see your hand in the design of how you formed and fashioned us. I ask this all in Jesus' name. Amen. So what we are going to turn ourselves towards is something called intermolecular forces, and we're going to look a little bit about liquids and solids. Okay? And the intermolecular forces is a total departure from Chapter 9. Chapter 9 is very math-based. Identify all the variables, find which variable you need to solve for it, done. Okay? This one, we're going to think a little bit more. The roll is roaming around. Make sure you get your name on the roll, please. So, I need to start talking about just a few things. Okay. If I write attraction, what does that mean? What is it? The pull of something. Yes?
Is it opposite charges?
Could be opposite charges. They attract. Okay? And so, attraction is a force that's pulling or attracting things together, but how many things? Can you attract one thing by itself? No. Attraction is a force. Well, I did not like that. Attraction is a force between two or more things. Technical term. Okay? Thingies. Okay? We're going to have thingies. And they're going to be able to attract to one another or not. Okay? And so, that is the focus. Now, a lot of times I'm going to draw for you a single molecule on a problem. Okay? And so I might draw something like this. And I will talk about how does it attract, or the attraction, the forces between this. Well, I drew one thing, but we have to think about it as one of those interacting with another one of those. I usually will not draw two of them because I'm a scientist, I'm lazy. And I'll ask you, what are the forces between those two entities? Okay? And I'll only show you one. Now, okay, what is the difference between those two things other than the spelling? Okay, one's inside and one is kind of external. Okay, which one is internal? Intra, yeah, inside. And inter is kind of outside, or inter means more than one. Okay? And so, if I do this, the force that holds the chlorine to the carbon here is a bond. That is an intramolecular force inside the molecule force. Okay? The attraction of this molecule to this molecule, how do these attract to each other, is an intermolecular force. Two different forces. Up to this point in time, we have only dealt with intramolecular forces. How is the molecule put together? Okay? And we had two main ways in which compounds are made. One in which electrons are given and one that is taken, and I become full charges, and there is a force in that molecule that attracts those two ions together to create a bond, and the molecule is those two forces pulling on each other. Or electrons are shared between, we use single lines in a molecular compound, and we're talking about the bond between the molecules to create a single bond. An overlap of electrons is a what kind of bond? Is it sigma or is it pi? An overlap between nuclei. Between the nuclei in the middle are sigmas. Pi's are above and below, like double bonds and triple bonds. Single bonds are sigmas. Oh, this is all come back. Finals coming at you. Okay. So, now I've just scared the mess out of you. I know. Okay. It's going to be all right. That's right. You will make it to graduation one day. Whether it be 4 years from now or
different major,
a different. No, we're not going to go to a different school. We may do different major, but I don't want any of my majors lost. Okay. So, intermolecular forces, IMF. Okay. Oh, sounds like we're in Washington or the military. The CIA, the NSA, the IMF, the intermolecular force, okay, is what we're talking about. Now, what really you can think about this is kind of like the forces that hold things together. Now, an intramolecular force holds the bonds, or they are the bonds between the atoms. These are strong, okay? If I give it a value in terms of numerical, for every mole, there is a certain amount of joule is a energy value. Kilo means 1,000 of them. 431 kilojoules for every mole to break the chlorine away from the hydrogen. That's a huge number. Okay. The forces that are between the molecules, an intermolecular force, are much, much weaker, meaning that there is attraction between two hydrochloric acids, but look at that number. It's only what? Only 16. It is small comparatively, okay? But it is important in how things interact in real life. All right? So I can overcome a intermolecular force, the force between molecules, without breaking the molecule down. I can add a little bit of energy and mess with how they interact amongst themselves, but I don't have to break it completely down. All right? All intermolecular forces can be called van der Waals forces. Okay? And we've seen van der Waal equation in gases where the intermolecular forces between the gas molecules became important because there was some sort of attraction between. Okay, so there are several intermolecular forces. They're classified as van der Waal forces, and then we're going to have at least 4 different kinds that we have to think about. Now, what do the intermolecular forces do? They influence how well the molecules stick together, okay? And we really see that in terms of how much kinetic energy is necessary to break those intermolecular forces. Now, when I say kinetic energy, what is the term or measurement that we use for kinetic energy? If things have lots of kinetic energy or a little kinetic energy, what is the measurement that I take in the laboratory? What is it? It is temperature. Okay? So that is where we talk about the kinetic energy, and so I'm going to add some sort of heat to the system, or I can take heat away, and based upon what the intermolecular forces are, how sticky they stick to each other, I might have to add lots of intermolecular forces to make it go from a solid to a liquid, okay? Or from a liquid to a gas. I have to overcome the attractiveness between those molecules, all right? But if they have very little intermolecular forces, then a little tiny bit of energy might make the molecules move faster and transition better. So we're going to talk about those. Okay. There are 3 major types, and one of them is going to get broken down into a subtype. So I will have eventually 4. Okay? Now, terms. Okay? Polar. We've used the term polar. All right? What does polar mean? Yes. Inside the molecule, one side has more electronegativity than the other side, and that molecule overall, there's a side that is a little bit negative and a side that's a little bit positive. It's not completely positive and negative, it's just partially positive, partially negative. Okay? And the molecule can be polar. Another term. I hate when that happens. Okay? Polar or dipole is a term that is used also. They are the same thing. Interchangeable. I have no idea why we use 2 different words for the same concept, just to mess you up. Okay? I guess that's it. And so if I say a molecule is a dipole, that means it's a polar molecule. Oh my goodness. How in the world do you determine if a molecule is a dipole? Well, if you have to determine it's a dipole, I have to determine if it's polar. And so I have to go back and draw the Lewis structure, look at each bond, decide if it's polar. If it's polar bonds, it can be polar, it could not be polar. It all depends upon its shape and if it cancels each other out. Okay? And so, here's the key. The types of bonds. This one is nonpolar, and we're going to see a lot of it, or X bound to X, nonpolar. There are less numbers of nonpolar types of bonding around. Okay? Any other type of bond is, the actual bond is polar, and many times that molecule becomes polar. Okay? So if you see molecules with lots of C and H's, those are the ones that are nonpolar. But if you see just about anything else, almost all the time, but not all the time, but almost all the time, there's going to be some polarity in there. Okay, and so I can represent a molecule like this right here, okay, in that there's a molecule in there, and I've determined that it's polar. One side's positive, one side's negative, okay? So if I have one molecule that is a dipole, it has the potential to attract to something else. And so if you have a dipole, you can have one of 2 things: an ion attracted to a dipole or a dipole attracted to a dipole. Okay? I'll talk about London dispersion force in just a moment. Anytime something attracts, they stick together. Okay? A positive and a negative get together. That's great. Energy is stabilized. You get a more stable structure. What happens is It has to have more energy to move around by itself, but when it partners up, it gets a little lazy and gives off energy. Okay? And so we can talk about energy being given off, or we can talk about it being stabilized as these things attract together. And it's usually the partial positive, partial negative. The more polar it is, the more imbalanced it is, the more charge on either side, the more attraction. So the bigger the polarity, the bigger the attraction. Also, the smaller the size it is, the closer it can get together, the more attraction, or you can talk about it another way, more stabilization or more energy is given off. So we want big time polarity, and we want really tiny size to get lots of sticking together. Okay? An ion dipole has an ion in the mix, a completely full charge. Okay? And if I do calculations, a full charge stabilized by a partial charge, I get a full big number and a little tiny number. When I multiply those together, I get a big energy. Okay? The other side, dipole. I get a little tiny positive and a little tiny negative, and I multiply little tiny things together, I get energy. But a little tiny stabilization. Okay? And so ion dipole is stronger than just a dipole. Okay? Because at least I have one full big charge, and then I have little tiny charges. The other one, I have little tiny charges to start with, but they can attract to each other, so I get some stabilization. All right? And so if I compare the two, ion dipole bigger, dipole generally smaller. The larger the dipoles are, the more energy I get. All right, London dispersion forces. Okay, here's the booger. Something that is nonpolar doesn't have a partial charge, so it doesn't attract to each other. Well, that's not true. Okay? Nonpolar interactions, okay, happen because we said that the attraction of the electrons between, let's say, a iodine and an iodine. The electrons are in the middle, right? And iodine is pulling, and iodine is pulling, and they're the same strength, right? And we say the electrons are right in the middle. They never move. Well, here's the problem. Electrons do move. Okay? They're always in random motion. Now, on average, they're right in the middle. But could there be a moment in time that the electrons aren't sitting right in the middle? Yes. And so for an instant, the electrons are imbalanced. So for an instant, a moment in time, it is unbalanced. So I get a little tiny charge for how long? An instant. Okay? The comparison. A dipole is a imbalance all the time. All the time they're imbalanced. The sides are always positive, always negative. In a nonpolar molecule, they have absolutely no imbalance most of the time. But for a second, they become imbalanced. They can attract for a moment, and then it goes away. But then another one happens. And so what we can have is the imbalanced nature of the electrons can cause a little bit of an imbalance for just a moment in time. And look, if one becomes imbalanced, like if I'm by chance holding here my electrons and I usually have them balanced, and all of a sudden I get all my electrons on one side, this side's just a little bit negative. This side's a little bit positive. And then I'm over here, a neighbor, and I'm like, what's happening over there? That looks a little positive. What am I going to do? My neighbor can become a little imbalanced because the person next to him a little imbalanced. If you hang around imbalanced people, you can become imbalanced. Okay? But hopefully for just a very short period of time. Because this one will then swing back, and then this one will swing back. And so you get attractions instantaneous, not completely all the time, so you get just a little bit of attraction between nonpolar molecules. The ability for a neighbor to make the other one imbalanced is called polarizability. Some molecules can be polarized easily, some can't be. But here's the difference with the London dispersion force. It's an instantaneous attraction for a very short period of time, and then it goes away. So you get a little tiny charge for a little tiny moment. So overall, it is a very, very small charge. Okay. Now, what we tend to have, what we tend to have with these van der Waals forces is this. Really tiny things, the electrons are balanced pretty well. They don't come and become really imbalanced. But the larger something is, the more electrons that there are, the more of a chance it can become imbalanced. So van der Waals forces kind of increase as we get bigger things, and they're smaller when the molecule is smaller, because smaller can balance out much easier. And so if we by chance get a force here where we have that not really very polar, as we get larger in mass, we tend to have bigger attractions because of this. For us to boil these things, it takes more energy as I get larger and larger and larger. This is because these are relatively not very polar, but as they get larger, they tend to have much, or tend to need much more energy. And so there's a trend here, and if I follow this trend, we can see that it looks good here, except for water. Water doesn't follow the trend. Water should have been somewhere around here. Water should boil, based upon this trend, somewhere about a negative 100 degrees. But water boils at a positive 100 degrees Celsius. There is something going on with water that isn't going on with other things. Okay? And so this is a subset. Something called a hydrogen bond is a dipole, but it's a very special dipole. Okay? It can only occur when hydrogen is bound to a nitrogen, oxygen, or fluorine and interacts with a nitrogen, oxygen, or fluorine from another atom. Now, the hydrogen bond must fit this definition. It must be covalently bound with a single bond to one of the atoms, and it must be shared with another one of those atoms that have a lone pair of electrons. Okay? Now, what's actually happening? The oxygen, fluorine, or nitrogen is very electronegative. Okay? It attracts electrons. How many electrons does hydrogen have? 1. And so in this bond between the oxygen and the hydrogen here, okay? Oh, you're not seeing anything. Okay. Oh, it's back. Between the oxygen, oh, well, that's not on it. Between the oxygen and hydrogen. The oxygen is very electronegative. That means the electrons are way over here. Now, what's left? If you take the 1 electron away from hydrogen, what is left over? What's the only other thing in hydrogen? 1 electron and 1 what? Proton. This becomes a very big positive charge. Okay? Because the electrons are being attracted to that oxygen or the nitrogen or the fluorine so much that hydrogen feels like it has nothing almost all the time except for its proton, which is very positive. What are electrons? What charge are they? Negative. And so this pair of electrons is very negative. And so a very negative pair of electrons is attracted to a very positive proton, and the intermolecular force is huge. Okay? And so I can have a hydrogen bond between something that has a hydrogen that has to be covalently bound to 1, and on the other one has a nitrogen with a lone pair, or an oxygen with a lone pair, or a fluorine with a lone pair. Any combination of those can happen. All right? And this is important. So when I relist my strengths, ion dipole is the biggest. Then hydrogen bond. Then dipole, dipole. Then London dispersion force. Okay? If I put a graph of these, and I put ion dipole, I put hydrogen bond, I put dipole, dipole, and I put London dispersion force. Okay? Ion dipole could be like this big. Hydrogen bond can be something like this big. Dipole, dipole can be like this big. And then London dispersion force is something like that. London dispersion force is really tiny. Dipole, dipole can start to be significant. Hydrogen bond is really significant in terms of amount of stabilization. And then ion dipole is hugely. Now, what if I put on this chart a bond, like the carbon to hydrogen bond? Okay, the carbon-hydrogen bond energy that holds the carbon bound to the hydrogen is so much bigger than any of these. Okay, but we're talking about the forces between molecules. Hydrogen bond for water is important because for each water molecule, it can hydrogen bond with 4 different other water molecules, because it has 2 hydrogens that are bound and 2 lone pairs, so it can make a structure and create a crystal structure. This is one reason why ice, when it forms a solid, it actually expands, because it creates this lattice structure, because all of these hydrogen bonds form. It's very important for life, whereas most things freeze from the bottom up, ice floats. This helps all of the fishes in the lakes and seas. If the ice is frozen, they can live below. It has a real fundamental importance. It also makes it not advisable to take a very hot Coke and put it in the freezer to cool it down, because what happens if you forget about it? It explodes. Hopefully you only learned that once in your lifetime. Okay. All right. So, conceptual principles. All right, this is the kind of problem I'm going to give. There is absolutely no calculator involved. For some of you, that's a sigh of relief. For some of you, you're going, oh no, I can't check my work. Okay, so here's the question. In which of the following substances is significant hydrogen bonding possible? Methylene chloride, CH2Cl2. Phosgene, PH3. Hydrogen peroxide, HOOH, or acetone, CH3COCH3. Okay, and so there's something left off of this, and I will add those for you. This is not completely right. There are 2 lone pairs on that. Now that is completely right. All right, I'm being a little bit nicer to you than CHEM-111 because I'm actually drawing the molecules out for you. All right, now this is what the question is saying. If this one and that one, if 2 of those are interacting together, can you have a hydrogen bond? If 2 of those are interacting together, can you have a hydrogen bond? So let's go back and say this one is just, let's call this one A. Let's call this one beta. Let's call this one 3. And let's call this one Y. Why? Because. All right. Which one of these will have hydrogen bonds? Now, talk to your neighbor and come up with, in groups of 2s and 3s, come up with you have to turn around, turn around and create a group of threes-ish, and come up with which one you think can hydrogen bond. Come on. Talk among your group. Okay. All right. When your group feels confident that you have an answer, raise your hand. Okay, this group has a hand up. Anybody else feel confident that they have an answer? We have one group that is confident. Okay, for those that are guessing, raise your hand that you come up with a guess. Okay, all right, some guesses. All right, I've got one confident, I've got several guesses. Raise your hand if you have absolutely no idea how to even approach this.
I was going through the notes, but yeah.
Yes, okay, all right, so here is what we have to remember. What is the definition of a hydrogen bond? A hydrogen must be there. Is hydrogens in these molecules? Okay, so we've got at least there's a hydrogen. But a hydrogen must what? Bond to what? Something that is N, O, or F. Is that it? No.
It has to have lone pairs.
Something has to have a lone pair. What has to have a lone pair? Something that is NOH. So the hydrogen bond is the interaction between these two things, the lone pair and the hydrogen bound to something. All right? Which one is the only one that can hydrogen bond?
B.
Not B, because there's no B.
Beta.
Beta. Okay? Amongst itself. Okay? Now, you might have to draw it a little bit weird to actually have it, but remember, is that the real structure of B? Looks just like that?
No.
No, because it's flat on a piece of paper and it's really three-dimensional, but it has everything that you need. It has an oxygen that has a hydrogen bound to it, and then if you take another one of those, it can line itself up with an oxygen that has a lone pair. Okay? All right. Which one here can have a hydrogen bond? Talk amongst yourselves again. Okay. What color?
Black.
Black. Okay. And so, which one was the one that was going to trick you up? The green one could maybe trick you up if you don't know the three molecules that it must be bound to. All right, let me show you one. Not this one. Okay. Let's earn some points for me. Okay, intermolecular force. Work my assignment. It will open up today. I think it is. Okay. All right. Okay. Number 9. All right. The question says, identify the molecule that has the strongest hydrogen bond. Yep. Your choices are CH3, CH2, 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 Cl, or HCl, or H2.
Didn't you say the strongest bond was
The strongest hydrogen bond. There are 3 choices, but there are 5 5 choices that we can have. What are the other choices that we can have? All of them have hydrogen bonds of equal strength, or none of them have hydrogen bonds. Okay, so which one? Let's see if we're right. Oh, okay. If you looked at that, there was nothing that had oxygen or nitrogen or fluorine. See that? No NOF. Or no FON.
No, keep it off.
Okay,
Be
NOF.
cool, though, baby. Be cool.
FON is too close to.
Fawn is close to fun.
FON is close to fun. If you find this fun, then it's FON. If you don't find it, it's NOF. Okay. Okay. ONF, if you do it some other way. Okay, so I have just earned 5 points. Oh, thank you very much. You have given me 5 points. Okay. So that's a totally different way of this chapter, right? Thinking through this chapter. Not like P equals nRT. Okay. All right. Ooh. All right. I want you in your groups. I want you to look at this chart right here and see what you can see. Identify for me the trend that you see. What was on a TRQ? A dipole moment was on a TRQ? And now it's being used? And now it's being used. So what is a dipole moment? I'm having a moment. I'm a dipole. Okay. It is how large the polarity is or how big the dipole is. The larger the value, the larger the imbalance, the bigger the dipole is. What? That would have been helpful for the TRQ practice? Okay. All right. So do you see a trend with that dipole moment between these molecules? As you go down, what happens? It increases. Okay. What is the value on this chart that tells me how well they stick together? How well they attract to each other? Which one of the columns tells me that kind of information? The boiling point. The amount of energy necessary to separate them, make them boil, okay, is a measure of how well they stick together. So what do you see as you go down? What happens to the boiling point? It goes higher. Okay? Is there any influence in these about its weight? No. In this case, the weights are all about the same, but the dipole moment increases, and if the imbalance for every single one of the molecules is more imbalanced, then what happens to its boiling point? It goes higher. That means the attraction between any two of those molecules is stronger the larger the dipole it is. Okay, that's great. Let's look at this one right here. Okay, can I have a dipole with these? Yes or no? You cannot. Why can you not have a dipole with those molecules? Because they are diatomic, and so they have the same attraction. Okay, what do you see in the trend, though?
Boiling point basis.
The boiling point increases as the molecular weight increases. What is the only attractive force that you can have with those kinds of molecules? Which IMF? Which of the four? Can you have an ion dipole attraction? Can you have a dipole-dipole attraction? Can you have a hydrogen bond? What are you left with? LDF, London dispersion force. That means I can be imbalanced for just moments instantaneously in time. Okay? The trend for LDF, or London dispersion force, the larger the molecule is, the potential more imbalance you have, the more attraction you can have. And so what we see is they get larger, the boiling point gets larger. Okay? What about these right here? Can you have dipoles with this? To even know if you have a polar molecule, you have to have a bond. Are these bonding? No. But they are molecules. So they're just got the nucleus and electrons. The only thing they can have is which? It's imbalance of electrons for an instant moment in time. That's the only force of attraction between these are London dispersion. And again, the increase in energy necessary to break them apart is directly proportional to their weight. Okay, look at this now. This is your thinking exercise. Pentane and neopentane. Okay, here's their definitions. All carbon and hydrogen bonds, or all carbon-carbon bonds. Also, the same number of atoms in each of these, and the same weight. Okay? So they have no difference in polarity. They have no difference in weight. There is a difference in their attraction to each other. How do I know that? The boiling points are different, right? Okay. Talk about why that might be the case. Which one is better, or which one attracts to each other better? The N-pentane or the neopentane? The N-pentane attracts to each other better because it requires more energy to break them apart. Why would this, that has the same molecular weight, the same bonds, and everything, why would that one attract to each other better than this one? Talk. Discuss.
Because like what? For instance, oil.
Okay, you want to ask a question? You want to clarify?
Can you ask a question?
Okay, so why does this one attract to itself better than this one? Because, look, it takes more energy to break them apart than this one. So this one, multiple ones of these attract to each other better than this one. There has to be a reason why. We've said London dispersion forces are based upon size, if they're all nonpolar. Well, they are exactly the same size. So there must be one more thing about London dispersion forces here. What?
It's a shape.
It's the shape. Okay? Why? All right, think about this. For you to have attraction, you got to get close together. Okay? Walk through any lobby at Lee University. Okay. If you have a molecule that is shaped this way, laying on the couch really close to each other, there's lots of interaction. I believe this is against the community covenant, but that's a whole other issue. But what if you have something that is round? Okay? How much interface can you have versus two things that are round? Because ultimately, this one kind of looks like a round shape, right? And this one's kind of like a cigar shape. I know, I'm using wonderful examples. All right. Here has a large surface to marry together, or to interact together, or to get together. Okay. Here, if you put two of these next to each other, only a very small fraction of the surface can interact with each other. because this has a larger surface area that can come together and actually touch, you actually have more attraction. So shape is part of this. If it can pack together tightly, very tightly, you get more interaction. That can pack more tightly and have more surface touching than this one. So London dispersion force, as the molecular weight goes up, the imbalance can be more. So you can have a stronger attraction for that instant. And if they are shaped in such a way that they can pack very tightly or get close together, the interaction is stronger. Okay? And it's all based upon the shape.